Okay, so we talked about the general solution to ODEs. Let's talk a little bit about what happens for homogeneous equations. There's actually an easy way to plug in for those with a kind of guess and check method based on the simple form that the solutions tend to take. So let's take here an arbitrary second order differential equation with constant coefficients. It's second order because we've got second derivatives in it. It's still an ODE because all the derivatives are with respect to x. The constants here can be anything you like. This comes up in a lot of different circumstances, so we'll see this a lot in the applications, but A and B are both constants, so we have like this, and it's homogeneous because if we set y equals to 0, it's solved in all, it's 0, 0, 0. Every term evaluates out to 0, so it's a homogeneous system. In that case, where you have constant coefficient homogeneous system, the solution always looks something like this, where it's y a e to the mx, great, and we're going to see how that plays out when we get to the polynomial in a second, but we generally would also have two initial conditions, or they could be called boundary conditions or initial conditions. In ODEs, we don't really distinguish between the two because we don't know what x is. Is it like a time function? Is it a space function? Doesn't really matter. It's just the thing, the independent coordinate. So let's call them initial conditions for now. But when we get to PDEs, or we could have both boundary conditions and initial conditions acting together in space and time, because we can take derivatives with respect to both, we'll be a little bit more careful about distinguishing between boundary conditions and initial conditions. And an initial condition for this system would often look something like dy dx evaluated at x equals 0 equals, say, a constant. Let's just call it, I don't know, capital A. And because this is a second order differential equation, we're actually going to need two of those. So let's do another one where we just say y evaluated at x equals 0 is equal to b. This one is called a Dirichlet boundary condition, or our initial condition, and this one is called a Neumann boundary condition or initial condition. Doesn't really matter too much. The point here is that we've got two different constraints on different parts of the y dependence, and typically it's either the value of y at the beginning or at the end or something like that, the derivative of y at the beginning, at the end, something like that. We could set the value of y at two locations, and that would be probably sufficiently enough information under most cases too. We'll keep doing those in examples, but for now I wanted to highlight that this won't be enough to fully constrain this system. We're still not going to know how to evaluate this coefficient out front unless we have these extra pieces. Oh, and actually, let me not use A again. Let's use capital C. Okay, cool. Why is this form so great? Well, we know how to take derivatives of exponentials. We can plug in, and right away we see that the second derivative of y with respect to itself is just y, and each time we get a factor of m that pulls down. So we can write that immediately as m squared times y, this one as am times y, because we have just the first derivative, 1 power of m, and then the next one is just b times y equals 0. All of them depend on y. If y is not a trivial solution, that is, if it's not equal to 0 everywhere, the case that we were thinking about before we were determining if it was homogeneous, then we could actually divide through by y at any place where it's not equal to 0, and then we just have a simple condition on all of the non-trivial solutions for y. And we can tell if we go over here and look at our initial conditions, our boundary conditions, that those if C and B were not equal to 0, it would be inconsistent with having a y that was 0 everywhere in space. So great, let's just go ahead and do that. We can cancel out the y's. And now look what we have. We've taken an ordinary differential equation and we've ended up with an algebraic equation. And in fact, it's an algebraic equation we know how to solve because it's just a quadratic equation. So we do this. M is equal to minus a plus or minus the square root of b squared. Sorry, I've done this in a crazy way, which I now have to remember to translate between them. It's minus 4 times the first times the last, 4ab, all over 2. And that's our solution. Okay, cool. That's not so terrifying. Well, what does this come up with? Well, there are two roots here, not just one. And so we're actually going to need to take one of these solutions for each of the roots. There'll be a y for the plus root and a y for the minus root, and we'll add them together. How do we know we can add them together? Well, this is a linear equation. So every term in it is linear, which means if we take two solutions and add them together, we still have a solution. So great. So we can write the combined solution as something like this. Let's put it with a plus sign to indicate the positive root, and that has the positive m plus, which is the positive root here, and then plus a minus e to the minus of the minus root, which isn't quite the same thing. And by this, I mean m plus equals minus a plus square root a squared minus 4b over 2, and m minus equals minus a squared minus 4b over 2. All right, cool. So we've got our two roots to the solution, and we've got a combination of them in this form. Okay, well, all right, we're getting close now. It's still a problem though. What if a squared is less than minus 4b and b is positive? We don't actually know whether these are negative or positives. But if we're, I guess, assuming that they're all real, but it's possible that m could end up being an imaginary or a complex number because this square root's in there. So let's look just at the form of this equation without going through all the details. If a squared equals 4b, if that part vanishes, then we have minus a over 2. Both of these would be the same, and we would just have a plus e to the minus a over 2 times x. And that would be the one that we'd have to fit to the initial conditions over here and see if we could get a consistent solution. If we don't have that one, if we have something that's non-trivial here, then we would get two different roots, and we'd have to match each of these coefficients so as to satisfy both of the boundary conditions. The boundary conditions don't affect the value of m. This equation, which is sometimes called the field equation, the equation that applies everywhere except for in the boundary or the initial conditions, that's the thing that sets the conditions on m. We choose m to satisfy this equation, and then we choose the a's here to satisfy these boundary conditions. Two-step process. Okay, but if we have, say, a positive root here and this is real, then we'd have some kind of positive exponential here and some kind of negative exponential here. And when we choose our different initial conditions, we'll be able to determine the relative magnitude of the two. Sometimes we actually don't even get that formal. If we're saying we're going from 0 to infinity, then we might just throw out the root that grows as you go to infinity, the one that has the positive root, presumably. And you just say that's unphysical because it goes to infinity. And so we might only preserve the solution that damps with increasing x. And we wouldn't actually need both of the initial conditions. In place of one of the initial conditions, we would instead have the fact that it remained bounded at infinity. Okay, what if this turns out to be a complex number? Well, look, what we get if it's complex, let's put the minus a over 2. That comes out front because that's common to both. So I could factor that one out. A plus e to the positive root. And I'm actually going to pull out the I and make this, flip the sign of this one, 4b minus a squared over 2 times x plus a minus e to the minus I 4b minus squared all over 2 times x. Take a look at this. We've got an e to the I and then plus e to the minus I. That's going to be a cosine because we've got both a positive and negative imaginary part at the top. Things could get much more complicated, and we could think of this as breaking this down into sines and cosines or hyperbolic cosines, hyperbolic cinches, all of those things, depending on how all these roots work out and what's convenient regarding these, evaluating the a plus and the a minus versus the boundary conditions.